Hello, everybody, and welcome to Handmade Hero Show. We code a complete game live on stream. We are going to take a quick second here before I get started programming just to mention the fact that I've pointed out that HandmadeSeattle.com, which is Abner Coimbray's conference that he runs, which he ran last year and everyone loved. He was going to run it again this year, but of course, due to the fact that we are currently in a pandemic, wisely decided that perhaps everyone getting together in a room would not be the best idea. Nevertheless, he changed things around and figured out a way that everyone can sort of get together virtually. And there's now going to be a Handmade Seattle that just won't be quite so Seattle. Maybe it'll be on Seattle time, but it will actually just be throughout the world since everyone can participate virtually. If you want to get tickets, because I know a lot of folks who watch this show knew about Handmade Seattle and probably came last year to the show in person, I would suspect. I know I certainly saw a lot of people there. You can go and get tickets now. Previously, it was just counting down until the tickets were available. The website, you could not buy them. You can now buy early bird tickets, and they just went on sale today. And 100. So last year, when people actually literally had to get on a plane and fly there, there were way more than 100 tickets sold. I think there was more like 300 tickets sold or something like this to the show. So 100 will probably not last very long. So if you do want the cheaper tickets to the conference, you're probably going to want to get in on that pretty soon, because I'm guessing 100 probably won't last very long, especially since now people don't even have to travel to go there. So a bunch of people who probably didn't go last year because traveling is very expensive and or, they have families that they're taking care of or something, they can't just up and leave for 4 or 5 days, whatever it takes to travel to the U.S. and so on. You really want to probably get on this soon if you want one of those 100 tickets. Now, if you don't need to get the discount, then that's fine. But again, since this year there won't be any travel involved, some people who maybe can't afford very much in terms of a ticket price, it's a pretty good discount there. You probably want to get in on that because it's a much more affordable conference now since you don't have to pay for airfare and hotel, right? That really takes a lot of the sting out of a conference as reasonably priced as Abner keeps this, which, by the way, I would take a minute to thank him for doing, because a lot of these conferences these days are absurdly priced. I don't even want to know what the game developer conference cost these days. They're like $1,000 tickets or something like this. It's kind of just highway robbery. So please take a look at this. You can go directly there by just doing handmade-seattle.com pound tickets. And I don't really think that the majority of the conference has probably even been scheduled yet. So there's probably going to be a lot of stuff added to it, but there's already people lining up for presentations, as you can see. A lot of them are people that you've probably heard of before, or who, in fact, I think Elizabeth was presented at the last one. So if you came to the original Handmade Seattle, you would have seen that. And then other folks on here you probably have heard of. This one's obviously people who've been doing a lot of handmade stuff that you've probably seen before. So, give it a shot. And you'll also probably recognize Alan Webster here from 4Coder. This is the editor that I actually use on stream. So yeah, it's probably not even really completely full of what the actual schedule will be yet, but it's already got a lot of people that you probably already know about participating, and maybe some that you don't. But either way, I guess I'd just say now would probably be a good time to get your early bird tickets if you need the discount, because I don't think that's going to last very long based on last year. So that's the URL. I will let everyone else take care of that. Someone will probably post it in the chat. If you have the Twitch chat up at this moment, I'm sure someone will post this link. So you can just go ahead and click on it and buy your tickets. I will now go do some programming, and we will just mention that periodically on future streams so everyone who watches the show knows about it and maybe can get the early bird tickets if they want them. All right. So let's get started. Why we don't have a subst W in there, I don't know. We just don't, apparently. Okay, so if we go ahead and take a look at where we were on the sort of lighting optimization side, we've, I think, done a really good job, honestly. I mean, the lighting's getting the major backhaul part of the lighting where we need to do our raycasting has just been getting faster and faster to the point where now it's actually quite efficient. And honestly, we could probably get a lot more bang for the buck now by just going over and doing the filtering work, because most of the noise and the squariness will just go away once we improve filtering on this thing. So in terms of improving quality, what I'm doing right now is not really the highest order action item. But the reason I want to go a little bit further with it is because it never hurts to have faster raycasting. You can always just cast more rays and get more accurate. Or just take less time and save more CPU for something else, or run on a lower end system. So since the lighting is by far the most expensive thing that we're doing, I don't want to stop just yet because we are not really at a point where I'm out of ideas. If I was, then I might say, well, that's good enough. Let's go over and start working on quality. But at the moment, I still am fairly certain that actually we can improve the speed quite dramatically with this this algorithm. It can be done much more efficiently than it's being done right now. So we're slowly shaving time off of this, and what you can see now from what we have is we actually do 8 rays in a loop. We then write 8 at a time. And that's our fundamental, sometimes people call these a kernel or something, like the main unit of work. I don't really care what you call it, but point being, we now have effectively 2 hot zones. One is this grid raycast function, which basically does all of the costly work involved in determining lighting transport. And then we have one more hot zone over here, which is, well, actually, I don't think that Fill Atlas border is expensive at all. It's really just this. So this function right here, you can see after we do, so full cast right here is what actually does the work of calling the grid raycast. We could just weld it right in here. We don't really need to have these, we can decomplexify that a little, but it doesn't matter. That function call is not costing us anything really at this point. And there's not a lot of optimization that's going to go on by slipstreaming those. So really what we end up with here is just 2 hot points. One is the grid raycast that ends up getting dispatched in there. And the other is this process here, whereby after we do the raycast, you can see we have to loop through and do this sort of production work to generate the blurred versions of our, excuse me, the blurred versions of our diffuse map. It's really the blurred version of our spec map, so we're kind of turning the spec map into the diffuse map, might be the way to say it, but either way, that's what we're doing. And so this, I believe, could get dramatically faster, right? And the reason that I say that is because if you actually take a look at, for example, the HH Life Prof results that we're getting right now, so if I go into, No. Yes. So if we take a look at the HH Light Prof runs and how expensive they are, you can see here that we're at something like 4.5 right now, and obviously that's numbers pretty variable because CPUs being what they are, it's not particularly deterministic, but it's hovering around 4.5 depending on what we do. If we just turn this off, so if we say, look, don't do that, right? And we run it again, we can have a slight we can have an idea of how much time is being taken for that, right? And so if you look, 1 full second of time, which is a quarter almost of our entire time, is spent doing nothing but updating the actual map, right? So when we look at this time, when we look at 4.5 seconds, actually only 3.5 seconds at most is being spent doing the actual work of computing the light transport. We're then spending a full second processing those results. So I just wanted to point that out because this is a massive opportunity for us to speed up this function here, and people were asking in the pre-stream how fast we think it will get eventually. They were like, they estimated they thought they would get to 3.8 seconds. I suspect 3.8 seconds is actually not probably plausible as a lower bound. I think we'll get much lower than that. And the reason I say that is because we have such a tremendous opportunity for optimization. Not only do we have that, but we also have the fact that we're still doing all this in floats, and we could just do it in 16-bit. So we could reduce the memory traffic dramatically as well. There's just so much opportunity that really the only reason we would probably get stopped at 3.8 seconds is if we just decided we don't care about getting it faster than that, right? So I think we're in good shape to shave at least another second off this, maybe get down to something like 3.5, but if you really wanted to go hardcore on this, you could probably get it even lower than that. I want to take a little bit more of a look at the actual raycaster, though. I want to do a little bit more work to see about whether it can be made a little bit more efficient than it currently is. If I take a look at this leaf index call here, this is one thing I really want to look at. So what I would like to know, we've already done testing about what happens when you flatten the cost metric, right? So if we wanted to know how fast this thing would be if it just has to run the code path but doesn't actually have to do anything. So I'll run with cost metric 0. We know that takes us from 4.5 to 2.2, which is pretty dramatic, right? So that means we are spending 2.3 seconds of our test run time doing the actual work in here on the cost metric. However, what I'd like to know is what happens if we have to just do one of them. So what you'll notice is that if I set the cost metric to 1, then we know that when we get through here, we'll absolutely decrement it at least to 0 there, which means that we will do one pass through the routine and then exit. And I'm very curious to know how much that costs. So if we run something, we know that 2.2 is the flattener. So what's really fascinating here, right? You see this is 2.6. That gives me a tremendous amount of insight into what's happening here. And it's exactly what I expected, which is great. It's what I wanted to see. So, the reason that I wanted to see that so specifically is that if you think, sorry, I'm still I still have the coronavirus or allergies or something. It's been going on forever. So if you look at what that's telling me, and this dovetails nicely with what I wanted to do to the routine, so that's what I was hoping to see. The thing that I didn't want was if I did that, it jumps back up to 4.5, right? I didn't want it to be that just running this code path once. I wanted it to be that it was the repetition of hunting through the grid squares that was costing us, because that's what I could do something about. I didn't want to see that just running the code path once was the expensive part, because if that was somehow true, then me improving the grid iteration is not going to fix it, right? Okay. So this is exactly what I wanted to see, and what that tells me is that actually this routine is quite sensitive to how many times it actually has to run the loop, which is what I wanted. And it's what you would assume, but I try when optimizing things, especially on modern processors, not to assume things, because oftentimes you'll find out your assumptions are wrong. So I like to get some confirmation that my assumption might at least be somewhat correct before, jumping to conclusions there. Okay, so what do I want to do here? Well, there's a couple things. So first of all, if you take a look at what's going on in this routine, you can see how it's structured. We do a little bit of testing to see whether we're still inside the grid, and then this is our heavyweight loop that just wants to loop over all of the things that we're going to intersect with, so possible occluders, and we're going to check against them. Now, what you will notice is when we hit, we immediately break. So if we can find a hit, that's the end of the routine. If we always found a hit on the first time, then we would be really happy because it means that we wouldn't have to keep running this loop. Now, maybe this part right here is the really expensive part somehow. I highly doubt that because there's very little code. This is all got taken out, so it's really just this part right here. So I doubt it because the part where we actually do the sampling is down here, and that's the part that would actually be the most expensive, and we're not running that only in the case where we hit something. We're running it every time. So really what that means to me is that this at least is part of the expense is doing this loop, right? And what you see is that running this thing repeatedly will cause us to keep going through this loop and then this post-amble. If we don't hit something, we're going to do this, and then we're going to run the loop again and so on, right? Now, if you look specifically at how this is set up, what you'll see is that it does intersections on 4 boxes at a time. And it has a loop construct here, which is designed to test 4 boxes at a time and then go to the next one. What that means is that ideally, because we have a branch in here, and we'd like that branch to do something, and we test 4 at a time, and so we'd like to test 4 at least, our loop is set up so that we would really like the occupancy of a grid to be in some sweet spot that's probably 12, 16 boxes, something like this. It's certainly not 1 or 2 boxes, right? And so I'm really concerned about this in the sense that I feel like if I go look, we're probably getting very low utilization out of this loop because the size, one thing we chose to do as sort of a simplification is to table drive the walk along the grid because I was afraid that that might be too difficult for me to write inside the loop. It might just take too many instructions or something like this. But the cost of that means that the table walk has to be aligned with the sampling voxel. And the reason that it has to be is because otherwise the table walk wouldn't be table drivable. If we could just raycast from anywhere, we wouldn't be able to table drive it because we wouldn't be able to pre-compute it, right? Now maybe we could come up with a different kind of table, but it's obviously way simpler to just say, look, we're just always going to go from the voxel. And that way, every place we need to sample, we know we just look up in the table and we're done. The cost of that is that now, if you look at how fine-grained our lighting voxel is, right, you can kind of see that, like, the squares of lighting, I mean, everywhere you see a differently flickering, or one of these, like, sampling lines here, because, our sampler's not very good right now, that's sort of showing you that the resolution of that voxel, and it's pretty fine-grained compared to our geometry. Like, there's just not very much geometry here. And sure, as the game gets sort of implemented, the gameplay gets implemented, there's going to be more, but there's not going to be that much more. This is not a game, like, there's going to be like one person, maybe tops, in each cell, and most of the time not even that, because there has to be empty space in these cells for the characters to move around. This is a sparse game. For gameplay purposes, you're thinking Legend of Zelda, it's not thousands of guys piled into a room. It's you and 3 other enemies with maybe some geometry in there for strategy or something, right? But an empty room like this one is not that far off from what we're actually going to have. We're just not going to have that much geometry per square. So having our grid be that small is really inefficient. We're probably only getting 2, 3 tops things per grid. We're not getting 8. There's just no way. right? So I think one of the biggest problems that we're having right now is we're just not getting any load out of this routine, right? So let me just prove that to myself, because I, again, don't like to assume things. When we're doing this sort of work, I would like to keep it as straightforward as possible and know what I'm getting myself into. So when we do our internal lighting core here, I would like to actually take a look at what it generates for its spatial occupancy and print out what the occupancy actually is. So I'm going to go through and I'm going to see if I can determine the answer to that question. So I'm going to do a loop, and if you take a look at the, well, you got to spell stuff right. If you take a look at the actual lighting solution itself, in here what you'll see is there's the spatial grid nodes and the spatial grid leaves. If we just walk over the spatial grid nodes, we will be able to see how many leaves there are in each one. And for each leaf, we can also look to see how many actual boxes there are in them by looking at, say, the boxmin to see, how many of them are filled, right? So if we go through, and I just go through each node index, and I'm assuming we can just count on the fact that the node count is what it is. So in here, Jimmy, here you go. You can kind of see we compute a total leaf count, and we should also do a total node count right here. There it is. So you can see here we can just do this get total cell count, right? So if I just ask it for the total cell count, I should be able to loop over all of them. And then I can look at the lighting spatial grid node. I can say spatial grid nodes plus node index. And if I now look at how many, I can basically keep two stats, right? I could say, okay, there's the total, total leaf, I guess we'll say node count. And then there's the total, well, these are both U32s, by the way. I guess I'll also say total grid node count. So I'll sum these up, and then I'll say the total box count, right? Well, actually, I know the total box count, so I don't really need to keep that. But I can do the min box count and the max box count. I don't really need this because, we know there's ones with nothing in it, right? And so another thing that I might want to keep is a histogram. So the other thing I could do is say like leaves, or rather nodes per count. And I could just say, look, let's just say we're going to take up to 64. Well, like none of these boxes are going to have 64 in them anyway. So we're just going to say, let's count a histogram and just print out the histogram of, how many of each fullness there are, right? So I can basically get a bunch of stats here, and this one's probably the one I really want. So I don't actually know if I actually care about any of these. So I might just say let's do this. So in here, what I need to do is I need to do a box count and produce this somehow. And then I need to say, like, well, look, if the box count is greater than or equal to no, well, actually, I can just, I guess, say box count equals the minimum of the nodes per box count array and the box count. So just to make sure we don't actually, like, go over. And this will actually set it equal to that amount, so I want to make sure it's actually one less than. So basically, like, we're going to insert 63 will get all of the overflow, so if somehow there's somebody with 100 in there, we'll stick them in the 63 box, and that's fine, because I don't honestly think there's going to be, but we don't need that. That was already, like, crazy high anyway, so it'll be fine. So then I'll just say nodes per box count, and I'll increment it, so then we know there was a node with that many boxes in it. And then when I'm done, I can just go through the box count one by one. And just print it out. So I can say, hey, nodes with, or sort of like, maybe I'll just do this, box count, you. And I'll just say, all right, the number of nodes with this box count was nodes per box count. And to avoid spamming with way too many lines that don't give any information, I'm just going to only do it if the nodes per box count, in this case, is non-zero. All right. So the problem we have now is we have to actually count, and counting is not trivial in this case. It's not hard, but it's also not just one line of code. The reason for that is these are packed. So what we know, if we look, we can loop through the leaves. So we're going to have to do something like this, right? And what we're going to have to do, actually, I guess we can use the loop that we have here. We've kind of already written it in the grid raycaster, right? But it looks like this, right? So we need to loop through the leaves, and it's easy to know how many leaves we have because it's just these two elements of the node. We can just look at the difference between them to find out how many there are. But the problem is we don't know how full each one is. So we could simplify our calculation here by only looking at the last one if we wanted to, meaning we know that if we know that every single one of these is full except the last one. So we don't actually have to do what I'm about to do, but just for simplicity, I don't care. This is not a speed-oriented routine. In fact, it's not even in our production code. It's just in the testing, the performance testing. So I don't care at all. I'm just going to write it by summing them each. So every time we pull a leaf out, what we want to do now is see how many of these box values are actually full, right? So I guess I could just do this wide, which sounds crazy because I don't care about how fast this runs, but honestly, it seems like since these are wide values, that's just the fastest, right? Like, that tells us how many of these things are zero, right? And I don't know if I can do that, can I? Oops. That's what I meant. There we go. Like, can we just do that? Do we have that? No, we don't. So we do have this, right? So I guess I'm wrong. Oh, those are V3s. So I think we can just do it just with one of them, right? So we can just say, are the x's equal? And that should be sufficient. That just gives us a wide vector. So this is like, and can we do this? So maybe I'll just say has volume. Well, that's actually already a function, so there. So I'm just going to do this test. That gives me back a vector register where each of the slots for the floats, so the 4 float slots, is all ones in the case where it's a valid box and all zeros in the case where it's not. So then I can just do a mask move, right? Or a move mask, I should say. And this will just give me back a count, right? So this will just be like, all right, that's the count. And in this particular case, it'll just be like it'll just be the bits are set, depending on whether the first bit's a 1 or a 0 based on whether the first one's valid or not, and the second one and the third one and so on, right? So I believe you can just do a population count in x86 because, oh my god, x86 has like every instruction. I don't actually remember what it is though. So it's this. Oops. Conveniently called pop count. And so then this is how many there are. So at that point, I think that's all I actually need to do. So I can just say box count plus equals valid count, right? Now, I think that might actually be everything, but because I slammed in some crazy SSE code there with population count and so on, I kind of want to make sure that this code works at all because that's kind of absurd. So let's just take a look and see if that's even remotely right. Because, yeah, that was kind of a crazy town thing. I just wanted to count because I was like, yes, you know what? It's probably just easier for me to write this wide. I didn't do that to be fancy. That's just what came to mind, you know? Maybe I'm writing too much SIMD code lately. I don't know. So let's take a look at valid. Oh, by the way, George, the person who wrote Remedy BG's X13 pixels on the chat, he reminded me of something that I always forget to do on stream, but that's really awesome. So if you notice, if you look at one of these things here, it's a real pain in the butt to like actually get down to the values you actually want to see. And so in this case, like we kind of probably want to look at this as a U32 because we just want to know what the mask is, right? You can see the mask was like these two are valid and these two are not, or something like this, right? So I kind of want to just see valid P that way, and it's kind of a pain in the butt to do this. Because it still sucks, like it's still hard to see and it takes up a lot of space and whatever. And Remedy BG actually has like way better stuff in there for that, so I guess I don't really know what the format specifier is for this though. Is it PS or whatever? What's the, how do I, you know, George can tell me how he'd do it because I never remember correctly. I need to learn to use some of the more advanced features of this, but it's something like that. I thought you just did PS. George, am I wrong about this? Maybe I shouldn't be using this feature yet. I don't know. Oh, it only works on the registers. Can I add a request to make it work on regular variables too? I know I asked too much of George. He wrote this debugger in his spare time, by the way. And it's the best debugger for Windows right now, right? Which is kind of crazy. I wish I was rich. If I was rich, I'd just, you know, ask George to quit his job and do the debugger full time and just be like, I'll just pay whatever your salary was. But, you know, that's something only rich people can do. Anyway, if you're rich out there, could you consider doing that for me? Because that would be great. So if you take a look at what's happening here, the population count feature seems to work just great. Let's take a look at the valid, if the valid feature works right. leaf box min max rather x. So if I take a look at these the old way, yeah, so that just worked. That is a tiny little sliver of a box, but that is actually correct. We probably should just throw out slivers like that, to be honest, but who cares at the moment. So anyway, if I now take a look at the results of this, which I now have some reason to believe might be sort of correct a little bit. Oops. Well, I probably can't do it that way. I probably got to do it this way. There we go. So if you take a look at the distribution of these things, what you can see is it's really not what I wanted. You can kind of see that, like, the numbers just aren't very high. I don't know what the optimal box load is. Box count 0's probably fine because we know that we're just going to have empty spaces in this grid. So, you know, that's not a problem. But if you take a look at the box counts here, you know, that's not great. That's not great. We really want it to be mostly, honestly, all of these are probably not great. We probably really want to see more up here, even higher than that, right? So this just, again, confirms what I was assuming. I really just wanted there to be some way that I could verify there's probably a speed win to be had boosting that occupancy. So where I'm going with all this is just one simple statement. Our grid cells are too small. We need our grid cells to be way bigger than the voxel, right? The lighting voxel. So our spatial occupancy grid size is way too tiny. It needs to be much bigger. But the only way we're going to be able to do that is by not table driving the walk. So what I want to try to do today is I want to see if I can do the walk inline, right? So if I go over to the lighting and we look in here, you can see this is what I'm talking about right here. So this bit here, so you can see here when it starts the walk, it does this walk table thing and it grabs the walk table entry, and then it starts walking through here, and it grabs using the grid index, which it got right out of the walk table, I believe. Oh wait, no, the grid index we know to begin with, right? Oh man, I'm out of tissues. Well, that sucks. Oh well. So if we take a look here at what what's going to happen with the grid index, we would need to find that somehow. So we'd need some way of finding. Oh my God, magic Kleenex. Thank you. So we'll need to find the grid index somehow, but that's not very difficult because we only have to do that once per bundle of samples. So that's going to be a pretty simple thing to do. That'll just be like, hey, tell me where we are in the occupancy here. So that's not going to change. That'll just flow through properly. So the only thing that we really need to do is figure out how we're going to get these two things to happen in line, right? So what I'm going to do is I'm going to just see if I can fast enough get the compute walk table code. So this is the code that we were doing here. Can I get this compute walk table code to run fast enough in line, right? So basically what I need is this. And what I'd like to do also is try to figure out the way to do this fast without introducing breakage. So I'd like to be able to test my results. So what I might do is just copy this and say, okay, let's take a look at compute walk table fast or something like this. if I were to not like take this dest part out of it, so we're not going to do we're not going to do this dest part of it here, and instead what we're going to do is, and we're not going to return anything. I'm just going to say, hey, maybe I'll call that verify. I'm just going to say, hey, can we just verify that the results are the same, right? So everywhere in here that we were doing something to dest, I'm actually just going to do something more like this. So we'll just say this is the t terminate, and this is the d grid value, which I think is what, a 16 or something like this. What's the d grid value? I don't even know. It's the step, so it's S16. So it's an S16 value, which is exactly what I thought. So we'll just do like a t terminate result and a d grid result. Those are these two things here. And then I just want to say, hey, let's assert that these things our, fast, quote unquote, computation is doing are correct. So this will allow me to generate the table the same way that I was generating it, and verify, and then I can start mutating the routine into something faster and see if we can maintain accuracy while reducing the number of instructions and so on, right? Just so I can boil it down faster that way first. So in here, if you take a look at where we're actually using dir, I don't need to write that because, again, while this is something we need to access here to get like the ray D out of here and all that stuff, I don't need to fill out that destination, so that doesn't need to happen, right? And I'm not returning anything, so I'm just asserting stuff. That's all I'm doing. And so I should be able to just do the test that way, right? So all I'm going to do is I'm just going to go ahead and take this compute walk table fast. And I'm going to call it, and in this case, since I'm just doing it in the lighting profiler, I'm not going to bother with it in the other place. I'm just going to do it right here. So immediately after, right, I'm just going to call this. So I'm going to take this, I'm going to duplicate the call to do it exactly the same way that we were doing it. And I'm just going to call it like this. It won't need a temp arena. So if I get rid of this memory, nothing should happen, right? And now we should be good to go. So in theory, I can now run hhlightprof and it will do, whatever it's going to do. And then if I went in here and intentionally induced an error such as, hey, t terminate plus equals 0.2f, now if I run it, we should get a fault, right? It should announce this failure somewhere. Okay. That's exactly why I did that. Do we have assertions turned off? Why did that? How is that possible? I'm so confused. I mean, what did I miss? Okay. So here we are in compute walk table fast. Okay. So our assertions are turned off right now. evidently, right? I mean, you watched it skip straight on over that, right? Someone want to tell me what that's about? Handmade internal and handmade slow are both on. Oops. Okay. Was it just a typo? Did I like accidentally not put both things in there? Oh. No, but that still would have been wrong. So how did our assertions get compiled out? Did I do... Oh, is this the one that has the lighting assert turned off? I don't think so. There we go. Okay. So we were just undoing that because since we're profiling, we made sure that the assertions are on. So okay. That's all right. I guess I'm not sure what I want to do about that exactly. I guess I'll just... hand code it. So I'm just going to put in my own assert here. Like so, right? And then what I'll do is I'll manually fault. And so this way now, I should be sure that anytime there's an error, we fault in theory. There we go. And so if I don't do this now, we should run clean. Oops. We should run clean. Yeah. So now I should have some confidence that I can measure. I may have to do a fuzzy equals for the float because we may not get the exact same t-terminate value. I just want to make sure I get close. So this may be too precise, but we'll cross that bridge when we come to it. So let's suppose that we were to take this this dim step bit here. This we don't care about because it's per array. So we actually can still table drive that if we wanted to, right? So this can come from a table, and we can, so I'm not going to focus on that. Here we have our starting location and our t-terminate. We have our cost loop, which will already be there. We don't, all this stuff is fine. So the first thing we see that needs adjustment, because you can see here, like there's actually almost nothing is actually even happening here. Really all we need to look at is this. I mean, that's the only thing that's really happening. So for doing this walk, honestly, we're just looking at the min here, right? So we just want to know what is the lowest t value. So knowing what's the lowest t value, is a bit of a conundrum. We already did one trick for this, for the raycasting, and we could use the same trick again, and that's basically to just use the first 16 bits of the float and ignore the last 16 bits. But I don't know if that's going to fly here. The reason I don't know if it's going to fly is because stepping along the grid kind of needs to be correct. We can't really afford to be just randomly stepping like into a place the ray doesn't actually hit just because we didn't actually do the test accurately enough. And, you know, maybe it's fine because you'd have to be so close to a corner or an edge in order for that to happen. It doesn't matter which one you step into first. So it's really tough to say. That's a really tough call to say, and we'd have to actually go do some testing to figure out, to be completely honest. However, what I will say is we do have a test now. Like, I'm running this almost as a unit test, honestly, so I can kind of just party on it if I want to. And if it never triggers, then I know it's no worse than the previous one for the cases we actually are using. Right? So could do that. So maybe I will try it. I'm going to start by not doing that because I want to make this be a little bit... I want to do this in steps, but okay. You know? Sure. So let's see how fast I could actually make this routine. If you take a look here, I probably just want to do this 3 wide. I can't really do it 4 wide because there aren't 4 things to do that I can see. So what I would probably say is if you look at celdim and at, these can just be vectored up. So I can just say, look, there's going to be a celdim for and an at for, and these are just going to be, you know, kept in registers because they can be. And then there's going to be a ray d4. So we're going to have the ray direction and the at and the celdim as things that we just save. And to do that, it's pretty simple because we have these values. So I can just load up the at as, you know, sort of a vector where I just keep the last lane 0. I can do the same thing for the ray direction. And the same thing for the celdim, right? And so at that point, this, which used to be 6 instructions, will become 2. So that's nice, right? I can just say, okay, celdim for minus at for divided by ray d4 is our new, like, T4. It's our new, like, set of T values. So this loop over the dim indexes doesn't actually have to happen, right? So then what I could do is say, well, now let's just look at what we're actually going to get there and say, okay, so suppose we then said, yeah, there's going to be like a T this value, and that's just going to be the extraction of each of these. So we'll do an extract 0 of T4, an extract 1 of T4, and an extract 2 of T4. And I believe I rewrote these to kind of do that or something. Right. I don't remember how we actually looked at these, but it's something like this. What is it? There it is. So it's convert F32. And so again, none of that's necessary in actuality, but I just want to take it one step at a time. So I want to make sure we can do it using the same kind of divide thing. So now we can just get rid of that and replace in this loop a use of this with dim index, and then in theory this should run the same way. And I may have to make those float compares fuzzy because again we're kind of changing how they're done. And so we'll see if I need to give them some tolerance here. But first I'm just going to see and make sure, because I could just not be doing this right. Let me just make sure I got a clean compiler. So I want to make sure that I actually look at the values first before I assume that I need some fuzzy float in there. Okay. So if we take a look at the verify for verify index here, and we just take a look at what these values actually need to be versus what they are. Yes, you can see that that's like totally wrong. So we're still a little bit off here. So the question is, what did I screw up there, right? Because it seems like that should have been fairly straightforward, but I obviously did not do it right, right? Looking at the values, it's pretty clear that I just kind of brain farted there. So you can't just do this, obviously, right? Like, I need to update the I need to actually update the @4. You know what I'm saying? So like, I don't really know how that should be done. It may need to be done a little more cleverly. For right now, I'm going to do this, and then we'll work on how we're going to do that. Okay. So it looks like we don't need a fuzzy float compare there. It looks like that produced exactly the same answer, so that's good. But let's continue to take this a little bit further before we do anything, before we take a look at the @4 part of things. So this stuff is pretty fast. Like, this part can be made fast, obviously. This part is less so. So that's going to require some thought. But this part right here, where we downshift, I feel like that's something we can work on. So if we take a look at how we pick out that dim index, that may give us a clue. And I'm kind of trying to think in my head also like how this is going to work long term. So you can see how seldom we would want to do a mask out here. This wants to be a replicate. So I'm just trying to figure out like what I would actually need. And it's a little bit tough. So the step value right now is like a table-driven thing, right? So the step value comes out of a table, and we need the index of 0, 1, or 2 to figure out what that dgrid result is going to be, right? Yeah, it's just a little tricky. I'm going to start by just doing that compare because I'm not feeling it right now. I'm not sure how I want to. I'm not like immediately like leaping to like, oh, I kind of know how I want to attack this. So I may sort of do a little fancy dance and put on my large pantaloons and just kind of like sauce around for a little bit to see where it takes me. You saw how we did this before. It was kind of a little like cleverness here, where we kind of did this HComp shuffler nonsense where I did a horizontal compare and all this stuff. We could do a similar trick, right? We could do this and get the answer out this way, right? Like I could say, hey, just do a one shuffle, right? So this is like one instruction, and then do the min pause, which is one instruction, and the extract, which is one instruction. So 3 instructions and get them into a general purpose register. We could try that. That should give the best dim answer directly, which is kind of handy. Again, don't really know if it will work. It may not be precise enough. I really don't know. But that's what we're going to try anyway. And so if we get best dim out here, then in theory, we should be able to just, to get that T best, we should be able to do another shuffle. But in this case, I'm not really going to bother quite yet. I'm just going to say, all right, we'll take the actual extract. I think we can do this in just the slow way, like, hey, give me the best dimmeth value, right? Okay. So I think this is possibly something that will work. I don't really know. We're going to use T4 for this here, and the HComp shuffler is what it is. Everything else should be roughly the same. Let's just do that. In fact, I think, can we even just do this? Yeah. So we'll give it a shot. I'm not optimistic about it, but we'll see what happens. So let's see how far off we are on this stuff. This is called dgrid results. And tterminate results, like so. So what's interesting about that is we're getting the right tterminate value, but not the right best dim here somehow. So what's the deal there? So a couple things about this. One, I realize we didn't account for the spare lane, so probably we're going to have to remove that 1415. So actually, I probably should fix that. Before we go any further, that doesn't look like this bug, but we can't actually test the final lane. The final lane has to be not there. That was probably already getting taken care of by like nans or something anyway, because... no, actually it wouldn't. Yeah, it would, because we divide by 0. Like, this is a divide by 0, right? Here. So. In fact, just to avoid that, we could... Well, no, because we know that the ray D value that we're dividing by here, any of those could be 0, right? So actually, probably what we would want to do here is actually make this be an invd. So we probably actually want to do that. I'm not going to do that yet, but I do want to do that eventually. Okay. So what I would also like to do is I'd like to run this so I can have the values from it. So for example, I would like to know like a tbest ref and a best dim ref. So I'd like to keep track of these values just because that will help me compare and see what the answer should have been and why am I getting a different answer, right? So I'm just going to take a look at these. So if I look at tbest ref and then I look at tbest, they're actually different. So that looks like, an issue, probably the issue that we're having. If I look at best dim and best dim ref, you can see that they're different. I'm curious to know what number we're on. So it looks like this is just wrong. In other words, we didn't have to. It's not like we got to some subtlety, right? Like we were like, we stepped a long way, and then we found this like one edge case. We did get through the first three, but eventually we got to one, and it wasn't sufficient. Again, that could be the case that actually there's nothing too erroneous here, but the precision of that comparison is just not sufficient. So, I'm going to have to do something fancier. So I really don't know how I want to do this. I'm just not sure. I need to have some way of finding out which of the values in here is the smallest, and I don't really know how I would do that. The brute force method is I can replicate the values into another register with them swizzled around, and then I do a comparison, and then I mask move the comparison, and then I look that up in a table to get me the actual lookup value. So, is it fantastic? No. Would it possibly work? Maybe. Would it be fast enough? Maybe. I don't know. If we look at what I actually need to do, the other thing I could try to do here is produce these values correctly, more directly. And this one is pretty straightforward. So I would never have to actually extract to get this one. I could just mask and combine the t values. But I am not sure. You can see why I was worried about this routine, right? Like, so here's another thought. Maybe I'm doing this the wrong way. Maybe I really want to do more of this out on the scalar pipe anyway. because what's that pipe doing while the rest of that routine has all of these floating point operations all up ons? So it could be that the goal here is not actually to do it or to keep it wide. It's to do the minimal amount of work in the SSE and then just try to transit it out to a general purpose register, right? I mean, you know, the problem that I see is just like it really wants to be float. So I don't know that that's really possible. Because it's like, look, the main thing we're doing is actually this. Like, yes, we do need this one value to come out into the general purpose registers to do stepping, but everything else is just happening in float. So it really does kind of want to be wide, you know? Well, I guess we just gotta get started on it. I mean, I don't know. I'm sorry, I'm just not seeing anything fancy here. It's not really my strong suit. Like, cross compares are not really my strong suit. I'm not super good with those. I haven't ever really, like, done routines that rely heavily on those. So wait, where is this min pause? Oh, it's down at the bottom. Yeah. So one thing I wonder a little bit is I wonder if you could somehow use two of these to extract the value. Like, I wonder if there's some way. You know what I think there is? So, riddle me this, Batman. If I were to first do a comparison in EPU 16 to see, oh yeah, this would work. Is it a good idea? I don't know. Is it a good idea? I don't know, but I mean, it kind of might be. So suppose you had two HComp shufflers, right? So you're looking at the high bits here, and the problem that you have is sometimes those high bits compare for equivalence, and you'd like it to test the bottom, right? So suppose I did this. Something like that. So what if I said HComp high and HComp low? So if I did two shuffles to put these into place, so this is actually 0 and 1 now, 4 and 5, 8 and 9, and then these are just 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So if I did two of those shuffles, which is not great because that's two cycles, those have to issue sequentially because they're both going to happen on port 5, which is ugly. But so those two happen sequentially. And then I could say, well, if there's equivalence in some of these things, then I mask. Of course, now as I'm saying this, now I'm realizing that's stupid, because how did I know they were equivalent? Because in order to get masks into the channel, first I would have had to do a compare anyway. All right, that was dumb. Never mind, take it all back. Because as I was going to say as well, you could just do when they're equivalent, we just compare the low 16. But how do you actually get a mask into that channel, right? Because in order to know that they compared equivalent, you would have had to have lined them up to do equivalence compares, and that's exactly the thing that I was trying to avoid, right? So, not great. Not great. All right. So yeah, I think we're in the position of having to figure out something that's going to be a little bit more costly and involve more shuffling, unless there's something that I'm missing. So if we have a T4 here that we've produced, it's free for us to reproduce one additional value in here. So I'm just gonna, it doesn't matter which one it is, I'm just gonna end up using X, because there's really no reason not to do that. So I'll get one extra channel out of it. And then when we do our shuffle, I can produce 4 comparisons at once, and we can then use the mask of that to probably tell us what we need to know. So if in here I say, okay, at 4, I'm sorry, not at 4, F3 2X, T4, like shuffle or something, and I do a shuffle 4X of T4. And here what I need to do is just produce comparisons. So, I don't know what it would actually be, but probably something like that, maybe. We'll see what we actually want in a second. But here's where we'll actually get our comparison. So this is our min comp here, where we would do T4, oops, having a bad keyboard alignment day. So there's our comparison. And then we would mask mov that, right? So we would say, move mask that. This is really just a U8, right? But, oh well. So if we take a look at what we need for this comp mask, we should be able to do, you look at that, it's like, okay, so we have to do one shuffle, one compare, one move mask, and then we have a table and we look up into the table. If I can make that work relatively well, then we should be okay. And in fact, maybe that argues against doing this sort of fancy trickery here, because it might end up being exactly the same number of instructions. Right? I mean, you know what I'm saying? So if you look at how this is doing it, it comes up with a better answer. Like, it actually gives you the actual answer. So, your tables are smaller. So like this table, for example, is only 4 entries long, but if we were to do it the other way, it would be like 16 entries long. Potentially. So it saves some space, but it's not as accurate. So I'm not sure we really want to do the fancy footwork. So we'll see. Anyway, let's see how this goes. So we're getting rid of this. The hcomp shuffler here is not going to happen, right? So what I need to do now is I need to find some way of getting the answer out, though. And so that takes a little bit more work here. And so what we're going to have to do is have some table that tells us what the answer is. And if you look at how we would do this normally, we would say, look, if at x is less than at y, then if at x is less than at z, best equals 0, best equals, excuse me, best equals 2, right? And then in the other branch, we would say if at y is less than at z, best equals 1, right? So it looks like, to be completely honest with you, we probably only really need 3 compares there. So honestly, we don't even need the final channel, it looks like. I mean, am I wrong? So it looks like we only really need 3 compares. And so what we could do is just say, well, okay, so, if we actually just did it this way, and then we wanted to do the shuffle, we need x to be compared against y and z, and then we need y to be compared against z, right? Oh, well, actually, I mean, I guess we kind of do. And in fact, I guess, can we just do this with, well, no, I guess we can't. Never mind. So I guess we kind of do want that, because then we can save one shuffle. Because if we want x to be compared to 2 different things, then we can do it this way. There might be some way we, no, because we can't. So we need at least one of these to be duplicated, right? So, yeah. We need at least one of them to be duplicated. So I think that's fine. There might be some other way to do it. Trying to think if there's another way to phrase this. I think that's right. So anyway, if I do the shuffle, this would want the at x and the at y compare would be here. The at y at z compare would be here. And then we just need an xz compare, which would just be this one, right? So I think that gives me what I want, and then my table can be derived just from that. Right. So at that point, I think you'd probably want these to be interleaved differently, because you'd want to just get rid of the final mask value. So you want to just have nothing in that 4th channel. So you probably actually want your thing to be interleaved as xy, xz. That looks like the more efficient packing. I mean, I could be wrong, but that just looks like what's right. So it'd be xyxz, xyxz, xyxz in everything. And so then what we would do is we'd say it's xyxz. So t this now is that extraction, which we'll deal with whether we ever want to do that extraction later. But here's our actual comp. It's just T4 less T4S. And then we just have a table, which is our index, our best table. I don't know. It's the best table. So in here we would say, all right, let's look at what these bit patterns mean. So we basically have 0, 0, 0. And we know that we want to mask off the top, so we're really just dealing with something that looks like this. right? And so that high bit, after we do the mask move of this, the high bit is going to be x less than there we go. So our T4S now gets packed as our T4 is X, Y, X, Z. Our T4S is now Y, Z, Z, right? And then X for no reason. And since we're doing a less than, if we want, we can just make it always not be true, so that way we don't have to bother even masking it off. So what we would do is, since we know Z is the last thing, we just stuff Z in there, and then I think we're okay, because then we know that that bit on the mask mov will always be 0, so I don't have to even mask it off. Okay, so our bit pattern here, we know is in this column, we have a X is less than Z. In the next column, right, that's the high bit. So the high bit is X is less than Z. The middle bit is going to be Y less than Z. And the low bit is going to be X less than Y, right? So if none of these things are true, so X, Y, so basically that would mean that Z is primal, right? Because X is not less than it and Y is not less than it. So we would pick Z in that case, right? In the case where X is less than Y, but still, I think, so if neither of these two things is true, again, it's just Z, because Z is still primal. In this case, Y is primal, so Y is less than Z and X is not less than Y. So we would assume that Y is the lessor, right? I would assume. Just trying to think if this table makes sense to me, but I think it does. If X is less than Y and Y is less than Z, but X is not less than Z, then we would assume that that Y is primal. Actually, is that possible? Because if Y is less than Z, then Y is the lowest of them, but X is less than Y. This is like what? So I don't know what that is. We'll just call that one. So then, if X is less than Z, but Y is not less than Z, and X is not less than Y, then Y would be primal, I think. If X is less than Z, and X is less than Y, then X is primal. If X is less than Z, and Y is less than Z, but X is not less than Y, then Y would be primal. If X is less than Z, and Y is less than Z, and X is less than Y, then X is primal, right? I think. I might have missed one there. I mean, one way to say it is that X can only be, so this tells us whether X is less than Z. So X should only show up here, and it does. This tells us whether X is less than Y, and so it should, anytime it's less than Z and Y, it needs to be true, which is what you expect. In terms of this row here, this is when X is less than Z, but X is not less than Y, then it's just going to be Y, right? And then in here we just have, look, if no one is less than Z, then Z is primal. Doesn't matter how X and Y compare, we don't care. And if y is less than z, then it only matters which one of these two is primal. And in this case, it's like we don't really know. We could say anything. So somebody here is going to get 2. Like we could say that's x, right? It doesn't matter because it shouldn't be possible. So some of these just aren't possible, right? And that's okay. Doesn't really matter. So anyway, once we have this table, we can look into it. So we can just say like, okay, best dim equals best table, mov mask ps of our min comp. And that gets us out the best dim that we actually wanted. We don't need any of this or that, right? And I guess we then just need to figure out how we're going to get our t-best. At the moment, this is not particularly good, so we probably would want to look up a shuffle as well, right? That allows us to just move the correct thing into place. So we'd want to do that eventually, but at the moment, I suppose I would just probably do this. So that we can start testing the other part of it, right? So let's see if that works at all. It clearly doesn't, which is fine. Let me make this an easier to read. So what I want to look here is at terminate results and dgrid results, and then I want to look at verify index.tterminate. And actually, you know what? Let's do it that way. Dgrid results and verify. So here are the values. And then we also would want to look at some of this other stuff. So we want to look at like what the best dim and best dim ref are. And then the t-best and t-best ref, right? I don't know. Wait, what? So, like, that's a... Okay. That's a bit scary. So I must have screwed something up when I did like the XY, XZ stuff. Like I must have pooped out. I must have pooped this out somehow. So if we take a look at T this, I wonder what's going on here. So this just looks completely busted. Okay. Oh, wow. So this was actually correct all the way up till some kind of very odd case occurred, it looks like. Because we actually went through a ton of these. All right. So this may be a little bit trickier for us to wrap our heads around, right? So looking at what's going on here, I guess we should maybe verify that this actually always comes out with something that I expect. So let's do in here something like, you know, get that comp mask. If comp mask is greater than or equal to array count, best table, we'll put in another hard-coded assert. So interesting. So we never get an erroneous value here, but we do somehow still produce a bunch of nan. Which cost are we on? So we're on cost 1, so we've only taken one step, right? And we've produced some nutso values somehow, right? Which is crazy. Can I see what our Ray D4 is? So the Ray D4, so why would there be an inf in this channel though? Like, that's a 1 value. So like, why would that have come out weird? That's obviously just, you know, we screwed something up. You know, why would that be inf? Because here what we're saying is the cell dim minus where we are divided by Ray D4. That should have been stepping properly the entire time. So something's getting like swizzled around XY, XZ, XY, XZ, XY, XZ. So I just want to look at this one a little more closely. So which one did we say this was? 135. I'm just gonna want to. I'm just gonna want to look at that one. So I'm gonna set a breakpoint for just that specific one, so I can watch it. I'm gonna say 135. So we're gonna set a little breakpoint on frou-frou. And then when we walk through here, I just want to see what the heck is going on. So if I take a look at what at is, it's, you know, pretty innocuous. Nothing weird going on there. We take a look at Ray D. Nothing weird going on there. Take a look at cell dim. Nothing weird going on there. So let's see what we get for T4 first timeout. And this is what we would expect. So we just have infs here. Oh! Are we? No, but we're not. We're correctly accounting for that. We do 0, 1, and 3 in here. So yeah, I don't know. All right. So min comp. What's our actual comp mask here? Our comp mask is 2. So I can see why it's 2, because negative infinity is technically less than 0.69, right? You know, like, I don't disagree. What I don't necessarily quite grasp is how that is a negative 0. So like the actual source sample's ray direction, it's actually negative 0. So I'm confused about 2 things. First of all, the confusion number 1 is, why is this coming through as negative 0, right? So I guess our table generator has some kind of a weird thing in it where it's like actually generating negative zeros for some reason, which I don't know why it's doing, but it is. Right? You can see there's negative 0 right there. But the other thing that's weird about that is why didn't the other routine also have the same problem? So when we went through and did that same one here, like, is it just because we happen to be choosing the opposite way around of these? Like, would it have picked the same bad answer, basically? Kind of curious, because that's really strange and kind of busted. So we kind of need to figure out what was going on there. I'm curious to know. So if I just changed this to this, would we have the same answer, actually? Oops, sorry. Right? You see where I'm going with this, right? So yeah. Like, the only reason we were getting a different answer there was because of some nonsense, right? So that's real messed up, and we probably should deal with that separately, because that's really not good, like, for obvious reasons, I think. Yeah. So, alright, so looking at the other one here, so it looks like terminate, dgrid result here is wrong, because we're doing best dim 1 instead of best dim 0 here. For the reference. So it looks like to match our reference code, we actually did have a preferred order. 0 gets preferred when nothing is true, right? So, like, in order to be exactly the same, I guess technically we gotta kind of look at this. Like, the way that our thing was working before is it would just do, like, whichever one was best. So it would do assume X. If Y is less than X, take it, right? If Z is less than whichever one you took out of those two, then take it, right? So that's what we were doing before. And I guess for sake of reference, because we don't care, I guess I should just make it be the same, right? So I want these to be the same. So the way that would work, if we were to compare these, it would really do the other way around, I guess. So it would look more like this, right? And what we would say here is like, look, if X is not greater than Z and X is not greater than Y, you would pick, because you start with X and then you say, if it's greater than Y, take Y. If it's greater than, then if it was greater than Z, take Z, right? So in this case, it wouldn't be. Here we would say, okay, X is greater than Y, so we'd take Y, and then Y is not greater than Z, so we would take Y. Then doing it again same way, we would say, okay, X is not greater than Y, X is not greater than Z, right? So this is like the same case, right? We don't care what this value is in this case. In this case, X is greater than Y, so we take Y, and then we say Y is greater than Z, so we take Z, right? So we're just doing it the same way the old routine did it. So here, X is not greater than Y. x is greater than z, so we take z. X is greater than, x is greater than y, so we take y. Y is not greater than z, so we take y. X is greater than y, so, x is not greater than y, so we take x. X is greater than z, so we take z. And finally, x is greater than y, so we take y. Y is greater than z, so we take z. Right? I don't know if I read that table off correctly, but that's looks like more like what it is, right? Looks like I missed something here though, because we're wrong right off the bat. Let me just verify it one more time. So we're trying to take the least one. So if x is not greater than y, we keep it. X is not greater than z, we keep it. So that seems right. X is greater than y, so we keep y. Y is not greater than z, so we keep y. Yeah. X is greater than y. X is not greater than y, so we keep x. Y is greater than z, we don't care. X is not greater than z, so we keep x. X is greater than y, so we keep y. Y is greater than z, so we keep z. Right? X is greater than y, nope, so we keep x. X is greater than z, so we keep z. X is greater than y, yes it is, so we keep y. Y is greater than z, nope, so we keep y. X greater than y, no, so we keep x. X is greater than z, so we keep z. And same here. So that seems right. So why is that not, isn't that correct? Doesn't that seem right everywhere? Like that looks like it should be producing the right answer. All right, well, let's find out why not. So it's wrong right off the bat. Like the very first one is wrong. So it's just totally wrong what I've done here. I thought I was imitating this table, right? I mean, isn't that what this table does? It starts with x, and then it says, it starts with x in t-best because t-best, this comparison always fails. So the first time through the loop, it's just x, right? Next time through the loop, it's saying, look, if x is less than y, oh, I've got that backwards. Wow. This stuff is too finicky for me. I'm gonna need more coffee if I'm gonna try to do this. So actually I need to do it sort of the other way, right? If I'm actually trying to produce the exact same thing as this, if I need to produce the comparisons this way. So we start with x. If x is less than y, did we like change this or something? This doesn't make any sense. It has to be greater, right? Did I do something weird? Yeah, it needs to be greater. Oh, so that wasn't my fault. Okay. When I was fussing with that routine, yeah, because that's I don't know what I was thinking there, right? It has to be this. If the best is greater, you know, it's, yeah, I don't know what's going on there. There we go. So I didn't screw up. I just, for some reason, changed that routine. So now we're doing it exactly the same way as the old one, and it's correct. So that's the good news, right? We don't really know how efficient it is to do it this way, but hey, it was pretty simple. It was just a shuffle and then a compare, move mask into the table. Yeah, you know, that seems all right. That gets us which of our steps we're going to use, and it also allows us to do this shuffle if we want to, right? We can have a shuffler in here, and we can look those up in serially, like, right? So we can do this, where we have this shuffle table, and we just say, okay, so it's 0, 1, 0, 2, 0, 1, 0, 2, right? Well, that's not quite right. So if you look at what this index is going to tell you, they're not packed that way. So 0, 1 is correct. So 0, 1, 0 is correct, but then 2 is actually always 3, right? So we don't really have we never get the second, we get 0 and 1 and 3, but we never get 2 because we didn't pack it that way. So then there's 2. Then I want 2, 1, 2, 2, so 2, 1, 2, 2. So now I can just do a shuffle EPI 8, and I can just get the value out directly. So I don't need to do this anymore. Right, in theory, I can now just use the shuffle table. And extract it that way. So now if I just check, I want to make sure I'm okay here. Did that end the actual run? Yes, it did. So what I can do now is just say, oh, all right, like stop doing this to get the actual this value out of this. We don't actually need to do it that way. What we could do instead is just produce the F34X T-best directly. So, delete that for now. And then we'll say that's just going to be mm shuffle EPI 8. And it's going to be out of the shuffle table for whatever the comp mask was. And again, I could have just used the best in, but I don't want to dependent. I don't want to have to look up into the table and then use the look up into the table to look up into another table. I want to just look up into both tables. So I made the other table slightly larger so I could do that, right? So that's all that's going on there. So if we do an M128i there, and I say, okay, like when we do the shuffle here, I just want to shuffle the T4 value that we had before. So, I want to shuffle this thing to get my T-best value out. I don't care about this anymore. So now I just need to do this computation. This allows me to roll at 4 improperly, and really this now becomes my only problem. Again, I'm going to take this one step at a time, so to avoid taking too many jumps, right? What I can do here is just say, all right, let's take this and do a convert. So let's just take the 0th value, doesn't matter which one I take. Let's just take the 0th value. Oops, that's not a... What did I do there? Shuffle table X is actually U8. That should be fine. This, however, probably needs to be converted. So let me... this is the really annoying thing about the way they do these this SIMD stuff. I absolutely cannot stand it. In Intel land, it's so egregiously bad. But oh well. You have to put in a bunch of nonsense casts for no reason. So like, I've got to do this. Did we make a macro for this? Didn't we make like a pshuff b macro? Oh yeah, macro times. All right, so it turns out we do. So we can just do that. All right. So now we just have the problem that t-terminate here again is not doing but what I'll do is I'll just do a convert to get that out temporarily, and this is again just me trying to take baby steps because I don't want to have to debug more than I have to, so I'm just making sure that I match each time through. So now what I can do is say, all right, so t-terminate could now just be 4 wide, like there's nothing that would stop that from happening. And Yeah. So I'm just going to go ahead and say F34T terminate. So I'm going to get rid of the F32T terminate here, and I'm just going to go ahead and keep the T terminate this way from now on. So we're only going to do a convert F32 on T terminate now to do the check, and everything else will not. Looks good. And then what I'll do is say, let's get rid of the other place we do. So the other conversion is here. So that one's pretty easy to get rid of as well. The only problem that we're now going to have is how do we deal with this cell dim, right? And there's a lot of ways we can do this. You can see us looking up. We've got the best dim. We know which one of these we're actually looking at. So we could continue to just table drive it, right, if we want to. It'd be pretty straightforward. But I just want to take a look at it just to remind myself of how we actually have these arranged because, for all I know, we could do something better there as well. I'm not sure. So let's just check that out because we're pretty close now to having this entire thing be done in very few instructions. It does take some tables, but the actual amount of work being done here is pretty tiny, and that was the whole goal. We can also probably get rid of some of these assertions here, because now that we're verifying the entire table, we probably don't need that, and we know asserts were turned off anyway, so let me just get that out of there, because we're actually looking at these. And furthermore, we kind of know that this is working okay, because we've already tested it, but in fact, I'll move this down here. So now we have it all in one place, right? Okay. So we look at the instructions here. There's really not that many, right? And that's pretty good. So the question is, can we now let's just loft at 4 out of here, because we don't want to do that every time. So if I was to loft it out of here, what would it look like? Well, we would then not want to do this conversion, certainly, right? What we would want to do instead is just do this as an at 4 plus equals, right? So we'd just be doing this. And now the only problem we're going to have is this, while I think this actually might work, okay, never mind. It's just really wrong, right? Because it's not wide anymore. And the reason I guess it wouldn't work is because the 2 should really be a 3, right? So this is actually the thing that's wrong. We can fix it, and just for testing purposes, just to make sure that that's the only thing that we've got wrong here. What I can do instead is do this. So if the best dim was 2, we actually need to do, you know what, I'll just do it manually. So we can handle the cases separately here, and I'll just hand write them for now, and that will allow us to verify that that's the only part of the code that we then need to actually make work properly. So in the 0 case, we need to do interleaved, so we need to do 0, 2. In the 1 case, we can just do 1, and in the 2 case, we have to do 3. Right? So those are the switch cases. What is the problem? Oh, whoops. So the cell dim is is just a regular thank you compiler. That was handy. The seldom is not that kind of a value, right? Okay, so now we just need to like make this work off of @4, like so. And I think we're good. Okay. All right. So now we're just left with one more question, and that's how is this going to work, right? So we need to perform this on @4. This is easy because it's just a wide add. We've already shuffled it, so it's no big deal. But this is trickier. So we need celdim, which we actually have up here, right? We need celdim to be correct. We basically need to knock out values, right? So what we want to do is do a mask and then a sub so that we only sub from the correct channel. Again, the easiest way to do this would just be to do it with a table of a masking table, right? And I don't actually know. I mean, I don't know. Like, I mean, that just might be. That just might be the easiest thing. I really don't know. So I'm just gonna say, like, if we were to do that, and we're just super table heavy now, which, you know, maybe is good, maybe is bad. I don't know. So if you look at what we would need to do here, effectively what we've got is look up into this table. We know for case 0, we want 0 and 2 to be masked in. So that would look like this, right? We know for case 1, we just have case 1, right? So we're just doing, it is what it is. So that's a straightforward one. We know for case 2, we just need to do 3. So it's almost where it actually, it's almost its index, but not quite. And then we just have 2, 1, 2, 2. So then we just have 2, 1, 2, 2, right? So this is our like mask table, and we can just load it in, and that would be it. So that's literally just like a minus equals. On @4, we can just write it like this. We need to do an AND here to make sure that we mask it off. But other than that, all we're doing is saying celdim will get subtracted, but first it'll get masked, right? So it's going to get masked by mask table. We'll load off the comp mask, and we'll just say, hey, I guess I don't know how we cast this thing. Load F324X, probably. Not the most efficient because it's aligned, so actually that's not great, but oh well. I think that's it. Right? I think that would do it. And I guess we'll find out if there's a bug there, and there is. Always so frustrating. So, but I think otherwise, I think we're basically there, right? So we just need to make sure this thing works properly. We know this does, right? So we can take a look at an @for reference on this one. Let me just double check my table to make sure I didn't do anything too stupid, and then we'll go from there. So when we're doing this and to do the mask out, again, just want to make sure the table lines up properly. So if we're doing 0, we need to do the 2 ones here and here. If we're doing 1, we only need to do that 1, 0 again, and 2. Yep. There's 2, 1, 2, 2. So that, I mean, that looks right. So I'm not sure what the problem is there. But we'll find out. So let's do this. Let's say if we were to do a comparison between these two, so now we have the correct @for and our @for. Let's just see what they equal, right? So I should now be able to set a breakpoint like here and just compare the two and see what we get. So here's my compare value. Here's my actual @for value. Sure does look close. Okay. So I'm guessing there's just some like really small difference somewhere. Like, excuse me. So somehow doing this will now magically make it be wrong, and yet I don't really know why. So let's take a look at the case where it's wrong, because I don't know what case that is. Oops. What the hey? Oh, I'm an idiot. So that's a plus equals. Although that should work still. Yeah, maybe, I don't know that I really am an idiot. I mean, maybe it was just off by like a fraction. So it could be that like because it did it in 2 steps before, I was off by like a low bit, right? So, I mean, I guess technically that means that if I just did this, everything would be fine. Yeah. All right. So I was just off by the like an LSB or something there, like, so, you know, oh well. Okay, so the sum total of all the stuff we have to do is this. Right? And that's not fabulous. I mean, it's not the end of the world, but like... Oh, that's fine. Throughput of 3 is probably fine, but you can see the latency on that is high, right? It's 11 cycles in the divider, sitting around 12 cycles in the divider, like doing its thing, right? So like, do I want to change that to a multiply by the inverse? You know, maybe. Because if you, it's a third the latency, right? Like That's going to take 11 to 12 cycles to complete according to that, right? And, you know, this is going to take 4. So it's like 3 times faster to not do that. And so the only question is, like, can we just do it because we don't care and the divider's not doing anything anyway? Or is this going to be like a super dependent thing? And it certainly doesn't have to be, but I'm worried that the compiler will do it that way because it's dumb. So it's a little tricky, right? But what I can say is, all right, so that's pretty good. You know, this is really nice and compact. It's a little table heavy here, but otherwise it's actually quite straightforward. And you know, this is just for testing, right? So it's really just these is all it is, right? So like 1, 2, 3, 4, 5, 6, 7, 8, 9-ish, 10-ish instructions. None of which, besides the divide, are particularly weird. So, you know, but I'm a little worried about that serial dependency. So, you know, here's a 12 cycle op, and then it lines up behind this, which is required to do everything else, right? So that serial dependency chain is not great, right? So that's why I think that maybe really wants to be pre-inverted, right? Like you just wanted to do 1 over that value and then do the multiply. So as the last thing I do today, maybe what I'll do here is I'll just say like, okay, if we run, and you know, I should, so if we run this whole situation in, you know, if we run this whole thing in inverted mode, does it ruin anything? So suppose I come in here and I say, look, here's the table builder that we're using currently, like the old one. And we can see that there's a divide in here by ray D. What if I just change that to a multiply by the inverse of ray D? You know, does anyone pitch a fit, right? So if I say, I've got ray D here, and I want inv ray D is 1 over ray D, right? I can just compute that value. And then over here, I can just say, well, let's multiply by that, right? So if I do that, is there any noticeable, like, can you even tell, right? Wow. The answer is yes, to say the least. So that's odd, and that may be because of those infs and weird things we have in there, right? So I guess I'm not sure exactly what is happening there, but let's say, I mean, let's just take a look here. So when we do this, let's do sort of a safe ratio on that. So let's actually just do it more like this. So let's actually do x, y, z here. Let's produce it that way. And when we do this multiplication, I guess the problem that we're going to have here is we don't actually want to step by that ever. So what we want here is the safe ratio actually wants to be high, right? So it actually wants to be a really high value. And I don't know exactly what we do there. We could just stuff it, right? We could say, Like, look, ray d x not equal to 0. Or I should say just greater than 0. If it's greater than 0, then it's ray dx, like 1.0 over ray dx, right? Otherwise, it's like, you know, some F32 max or something, right? So we could do it that way, or you could even just say, look, it's some number that's way too high to ever be the span of a cell anyway, right? So you'll always hit one of the other ones first. So we could try something like this. I'm not sure if that'll work or not, but we'll see. And that looks like it's more or less right, but it definitely has a weird bias up here. You can see it doesn't really get out that direction. So there's some weirdness happening there, and I would imagine that has to do with the way that I've written this. Oh, duh. You know, that's just because we're not doing this part. Yeah, that was just dumb. There we go. So maybe I could just do it the other way. Let me just see. So assuming that I do the inversion here, and we're fine. I was going to say, like, that was strange, right? And it's just because I forgot we were doing that sort of preconditioning. Okay, so if we assume that we're going to generate the table that way, then I could also sort of eliminate this part of it, right? So now if I went back to HHLightProf and I compile and test those two routines against each other, I should get a failure because I'm not doing it that way, right, in the second routine. But now if I pre-compute my inv-AD, so I say, look, inv-AD4 equals, you know, 1.0 divided by RAD4, right? And then we change this to a multiply by the inverse, like so. Then what happens, right? Can we get them to match now? And we can. So I think that's worth doing because it doesn't really change the quality of the result that much, I don't think. And that makes this serial dependency chain less bad because it doesn't have that really bad like op like right at the head end. So now we're pretty good, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 instructions plus the lookups. Is it the most fabulous thing in the world? No, but like if we can trade 10 instructions in the outer loop in exchange for being able to set arbitrarily large grid sizes, that seems like really good. Right? All right. So let's go ahead and go to brief Q&A. Tomorrow we'll roll that into the loop and we'll see what we get. Because if we can roll that into the loop without taking too much of a speed hit, then we can go widen up the thing and be in good, right? Could you briefly say what the focus of Handmade Hero was in the last 3 months? Sure. Basically, what we've been doing is streamlining and optimizing the lighting transport code, which is the hardest code, really, in the whole engine. So I mean, it's hard to really summarize everything we did because a lot of it's very specific. Like, a lot of stuff about looking at like how something is working and what kind of spatial occupancy we wanted and how do we, what are the ways we can compute something and how do we roll that into 4 wide versus 3 wide versus blah, 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 right? So I don't know that there's much of a summary I can say other than like actually looking carefully at code and optimizing it was mostly what we were doing, but the specific steps we were taking are pretty varied, right? Anyway, I'm glad to hear that you're feeling better as a separate issue. Hello, Casey. This question may be off topic, but it's really important for me. Okay. I know you were doing some UI development. I saw your video on immediate UI mode. I have the only job opportunity to develop UI for a mobile app, but I've never did that and I need this job. So can you please give me some advice on where to find information? Maybe some guides on UI development, and we're using a library. So I really can't help you, I'm afraid. I don't use like all those like mobile nonsense, like web UI things. So like the job that you're going to be trying to get is going to want you to know like React.js or something, right? Or whatever the latest stupid JavaScript framework is, or like some Swift thing written. I mean, nonsense code built on giant piles of million-line libraries, right? And so I would probably say, if you can, since you obviously know, since you obviously know the company that you would be getting this job opportunity with, can you find out what kinds of stuff they would probably use? Like, can you go see what sort of dev they tend to do? And then you could look to find out what giant pile framework they're using. Just go watch the like crappy tutorial on it. Right? Because it's just going to be a giant pile of disaster. And as long as you're just familiarize yourself with that pile of disaster, you'll be as good as anyone else at it, right? So the only advice I can really give you is see if you can find out what kind of disaster pile this company uses for their crappy mobile UI or whatever, and use, brush up on that, right? I mean, with any luck, you can find, if you're trying to get a job with a company, you may even be able to find some like blog post that they've made that says exactly what sort of stuff they're using, right? And then you can just make sure you know that. What's the best way to debug something that only happens in optimized code? I mean, I guess I don't know. It's the same as debugging stuff that happens in debug code, just a little harder to read. You should learn to read assembly language, obviously, because that's typically pretty important, because the debug information that's output with optimized code is usually pretty bad, so you kind of have to be able to follow, but how expensive do you think the table lookups are? Well, table lookups are free. They're either 1 cycle or 0 cycles, right? So typically when you're talking about the cost of a table lookup, you're not actually talking about the lookup, right? You're talking about either the cost of computing and putting the offset into a general purpose register, because SSE doesn't have scatter gather, or you're talking about the cost of the amount of L1 cache that the table will take up that you then can't use for anything else, right? So like table lookups don't cost anything. They're free. So if you magically just had infinite L1 cache, and wouldn't that be nice? And you could do scatter gather, you would just always use them if you could, because they're always free, right? It's just free. But the problem is that you care about how much space they take up, so you have to be careful. And getting things into general purpose registers costs you something. And computing the index may cost you something too. In this case, it doesn't really cost us anything above what we probably would have already been doing anyway. But I mean, the MOV mask is not free, right? So you at least have to spend a cycle getting it out there before you can even use it, right? I don't know what the throughput of MOV mask is. That's not what we're looking for. So 3 cycles of latency, not that bad, right? But again, like way, way, way more expensive than the table lookup, right? The table lookup is either either free if it's a memory operand, because it will just come with the cycle that you issued the instruction on, right? Presumably. And so it's free to issue, but will have one cycle of work to do. So, depending on how you want to cost that. So it's either free or one cycle, depending on how you look at it. But this is 3 cycles just to get the thing in there that I need to look it up, right? So you can see that like the table lookup isn't the thing usually. You usually just don't care about that. If you're actually caring about the cost of the actual table lookup, something weird is going on. Usually what you care about is the fact that the table, which will be hot because it's always getting looked up into over and over again, however big that table is, it's just sitting in your L1 and you're using that amount that you can't get back, right? Because now your L1 size that you're using for everything else is now smaller. So if you magically have 128K of tables all of a sudden that you've created, you've blown out your L1 and your L2, well, at least part of your L2, and everything's way slower now because your tables are taking up all of your cache, right? So it's really more about that. It's really not about it's usually not about the cost of the lookup. Can you give a general idea of how to optimize branches out of a function? Yeah, just go look at, we've done that on Handmade Hero like a bunch of times, right? The concept's very simple. You just compute both branches and then mask the results together based on the comparison, right? So if you have, another way to look at it would be, we even did it today. So we did a more complicated version, which is using a table to produce the results. Usually you can get by, most things you can get by with just doing a mask combined. But this was the code we needed to execute, right? It's 3 branches. If, the first time through the loop, second time through the third time through the loop. We just replaced it with a move mask and a table, right? So now there's no branches in here. So you watched me do it, right? So it's basically just the process of turning things that used to be branches into computations that still produce the same result by just doing the work that would have happened on all the branches and making sure that the equation multiplies those out or masks those out, right? And that's it. Hello, thank you for all the vids. I'm a bored CS student that aces exams and now does know what to do on his vacation. All right, cool. Well, glad we could help. What kinds of things would you like the compiler to do to help with this table stuff, if any? John's compile time code execution is pretty good because I just write the code that generated this table instead of generating the table, right? Do you explain the compile time execution we haven't tried? Yeah, it runs the code at compile time. Would meow hash be suitable to create a custom UUID? It wouldn't be part of the UUID spec, but it could serve the same purpose. I'm not sure what you mean by UUID. All right, I'm gonna end it here. I should say we'll end there. Thank you everyone for joining me for this set of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow the series at home, you can always go to handmadehero.org and pre-order the game because it comes with the source code already, so you can play around with it as we are doing it. I pretty much set you up for success today if you want to go make the routine stop being table driven and start actually just running the grid steps directly. Because I just did all the work, and so all we need to do is just now go import that work up into the actual grid walker so it stops reading from the table and just calculates the stuff in line. So you could do that if you were so inclined. So think about it. That's about it for today. I'll be back here tomorrow to do exactly that, so see if you can beat me to it. Until then, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.